Up to this point, we have only been working with motion in one dimension. So basically, we've been constrained to the positive x and the negative x. Now we're going to start looking at motion in two dimensions, which means we're going to have basically the entire 360 degrees with which to work in terms of what directions our displacement and our velocity vectors could go. So to give you a quick example of what this might look like, up till now we've had maybe a displacement in the positive direction of 3, 4, 5, 6, and then maybe they go back in the opposite direction, 6, 7, 8, 9, 10, so then negative 10 meters. And so if we were using these two displacement vectors and trying to determine our total displacement, our total change in position would be negative 4 meters. Right, and we could represent that with an arrow here. Okay. Now, though, we're going to use multiple dimensions. So let's do some erasing. Where's our eraser? Let's get rid of this, and this, and this. So now, let's say that we have a person moving, walking, skating, whatever, and they go 1, 2, 3, 4, 5, 6, 7 units in that direction, but then they go 8 units up. Okay. So remember that displacement is the total distance from the starting position, and it also includes direction. So I'm going to draw an arrow that represents the displacement, the net or the total displacement of this object. It's going to be this blue line here. Okay. And so we need to still be able to find a value for this. Well, if you notice, we have actually now created a triangle with two legs of 7 and 8, and the hypotenuse of our triangle is the net displacement of our object. Now, in this terms that we're going to use, the legs of our triangle are what we call the components, and the hypotenuse is called the resultant. And so the hypotenuse in this case just happens to be the total or the sum of the two components, the two legs, the two individual displacements. Okay, we want to solve for the magnitude, so we're going to use Pythagorean. So we're going to say a squared plus b squared equals c squared. So that's going to be 8 squared plus 7 squared equals c squared. So c, our resultant, is going to equal the square root of 64 plus 49. And so our net displacement is going to be root 113. I don't have a calculator right now, but typically we're not going to leave our solutions in radical form. You're going to use a calculator, get it to a decimal, and leave it in 1 or 2 decimals, or leave it to like the tenths or hundredths place. Okay. But that's not the entire displacement, because we also have to address the direction. The easiest way to address the direction is using angles, and for our purposes, the positive x is going to be our 0 degrees. We are going to get bigger going in the counterclockwise direction, so the positive y will be 90 degrees. the negative x is 180 degrees, negative y is 270, back around to 360. So we want to find this angle theta to give the direction. And at this point, you can use your favorite trig function. You can use sine, cosine, or tangent. Let's just say inverse tangent of opposite over adjacent. So that's 8 over 7. And again, I'm not entirely sure what that is in terms of calculators and decimals, but we can figure that out later. So that gives us our angle. Now we have a magnitude and a direction. So that's for displacement. Let's take a look at velocity and look at some velocity components. So what I have set up here is a cart. So our yellow cart here is going to be starting at this point right here on the floor. It's one of our constant velocity carts. I'm going to turn it on and it's going to move to the right. At the same time it's moving to the right, I'm going to be pulling our Red River downward. And so our two velocities, our two components here, are going to be the velocity of the buggy, which is going to be to the right, and the velocity of the river, which is going to be down. I'll draw a quick diagram here, and we can get at least a sense for what it should look like. So we have VB, we have we'll call it VR. So our resultant velocity should be something like this. So what that means is that the net motion of our buggy should be something along those lines, down at an angle. So let's go ahead and play this. And we can see, that is wonderful, that our buggy finishes down here. And so there's actually our net displacement. We have a component in this direction. We have a component in this direction. And remember that we're talking about velocity. Velocity is simply displacement over time. Right, velocity is delta, actually let's say, let's do d over delta t, delta d over delta t. So our displacement is represented by our blue line, and we have some time. And so if the blue line is the displacement and the velocity always are going to be in the same direction. Because velocity is displacement over time, the two things always have to be in the same direction. Let's write that in there. So displacement and velocity are in the same direction. Okay, let's see if we can rewind that. So one more time. So what we should notice is that there are actually two separate velocities. There's the velocity of our river, there's the velocity of the car, of the buggy. Those two velocities are occurring independently of each other, but at the same time, and they're both impacting the net velocity of the buggy. And so this is what you're going to be using to approach the river problem. It's going to talk about the river problem on the very last page as you're working through that. Now, last thing to address. Just a quick overview of the final problem on WebAssign. And I don't remember the specifics, but basically it gives you like 5 or 6 different displacement vectors. And so it might say that you have one that's 20 meters at an angle of 45 degrees. And then the next one, they travel 30 meters at, say, 280 degrees. And then it travels, let's say, 80 meters at 30 degrees. All right, and so what you have to ultimately do is determine the net displacement in this case. So, best approach to this is to break all of our resultants down into components, because if you have your components, you can add all of your x's together, your x components, to get a net x value. Then you can do the same thing for your y's. And so what you'll end up with is some net x displacement. You'll end up with some net y displacement. Those become your components, and then you can solve for the resultant. The only thing you have to keep in mind is that for like this green one here, the y for the y component for our green displacement is positive, but the y component for our blue one is negative. And so when we add those together, you're actually adding a negative value, and so we ultimately end up subtracting because they're in opposite directions. So when we break up our resultants into their individual components, we can add our x's, we can add our y's, just like we've been adding vectors in one dimension, taking into account the positive and the negative, and then we combine them together as an x and a y component to find our resultant. So that's kind of a quick and dirty hit on two-dimensional motion and resultants and vectors. We're going to talk more about it as we go.